Yo, welcome to the video for Working Energy Assessment 2. I know many of you want to still reassess on that. I want to make sure that you had some information from me in case you missed it before we left school. So let's just jump into it right now. Number 1 says, how much energy is in the system and how do you know? Well, I think an easy way to start this problem is to just draw the pie charts. So here's the diagram. This is A, here's B, here's C, and here's D up here. So let's draw the pie charts for A, B, C, and D. And one of the things about the pie charts that we know is within our ability to draw them, they should all be the same size. So if I can figure out the amount of energy in any one of them, I know that's the total amount in the system. So we know this one is all gravitational. This one here is at B, it's 1/3 gravitational. Here it's 2/3 gravitational. This one's 2/3 kinetic, this one's all kinetic, and this last one over here, this little section here is elastic energy, and that's going to be important later. So number 1 says, how can you calculate this? Well, the easiest way to do it is to just use your gravitational energy formula. So the total amount of energy is equal to the gravitational energy at A, which is equal to mgh at A. And these are all things we know. If you read the problem, the mass of the cart is 100 kilograms. The g is the gravitational field strength near the surface of the earth, that's 10 newtons per kilogram. And the height, if you look here, is 30 meters. So this is 30,000 joules. And joules is the unit we use for energy. Number 2 says, how fast is the cart moving at B? Well, let's look at the situation at B. It's 1/3 gravitational and 2/3 kinetic. Now, you can get that from the heights. You can also just use this idea, okay? We know that the total amount of energy stays the same. So at B, the E total is equal to the gravitational energy at B plus the kinetic energy at B. And from this, we can actually plug and chug a little bit and see what we know. We know the E total is 30,000 from here. The gravitational energy here is mgh at B plus 1/2 mvb squared. And this is what we're trying to solve for. We're trying to solve for the speed at B. So if I plug and chug this bad boy, the mass is 100, gravitational field strength is 10, the height is 10 plus 1/2 100 times v at b squared. This is 30,000, this is 10,000, so this is 20,000. Half of 10 is 50. Now, this is, you can see this 20,000 is the kinetic energy, and we can also get that from the pie chart. If you know that the total size is 30,000, 1/3 of it is gravitational, the 2/3 is kinetic, so the 20,000 is the 2/3. 20,000 divided by 50 is 400, so V at B is equal to 20 meters per second. Three says, the spring over here has a spring constant of 5,000 newtons per meter. What does that mean? If the spring constant is 5,000 newtons per meter, the question says, write a sentence that explains that. Well, what it means is that if you want to compress this spring, a full 1 meter, it will take 5,000 newtons of force. So that's the idea there. That's what the spring constant means. It tells you how strong the spring is. This one says if you want to compress it 1 meter, it would take 5,000 newtons. That's what the spring constant is. Number 4 says, how far is the spring going to compress in this situation here? Well, again, the thing that we know is the total amount of energy. So I know that at D, the total amount of energy is equal to the gravitational energy at D plus the elastic energy at D. So we know that the total amount of energy is still 30,000. The gravitational energy is mgh, the height at D, plus, what is the elastic energy formula? It's 1/2 kx squared, where k is the spring constant, and x is the compression distance. This is what you're solving for. So if we plug and chug this bad boy, the mass is still 100, gravitational field strength is still 10, the height at D is 20, plus 1/2, the spring constant is 5,000, and then that's what we're solving for. Now, again, you could have used the size of the pie chart. The total is 30,000, 2/3 of it is gravitational, that's this, we're left with 1/3 for elastic. So this is 20,000, so 10,000 is the elastic energy. 1/2 of 5,000 is 2,500. And we can see 10,000 divided by 2,500 is 4. Take the square root. X is equal to 2 meters. So this is the compression distance of the spring. It's 2 meters. Five says, if this is a situation, what is the maximum amount of force that the spring applies? Well, one of the fundamental labs that we did this school year is we did something called the Hooke's Law Lab, where what you guys concluded from the Hooke's Law Lab was that the force exerted by a spring is equal to the spring constant, little k, times x, which is either the stretch distance or the compression distance. So if I want to find the force of the spring, I'm going to take the spring constant, which we know was 5,000, and multiply by the compression distance, which was 2 meters, and we can see the force by the spring. $10,000 newtons. Six says, well, yeah. Six says, how much force would you have to apply to the spring if you wanted it to compress twice as much? So if we come back to this Hooke's Law here, we can see the force by the spring is equal to kx. What we'll notice here is that the relationship between the force and the spring constant is clearly a linear relationship. So if you wanted it to stretch twice as much, you're going to need twice as much force. Times 2 here would give you times 2 here, and you know that because it's linear. Seven says, while bringing the cart to a stop, does the spring do work on the cart? And the answer is yes, it does. If we go back and we look at this arrow between them, we know that as it rolls from C to D and hits the spring, we know the gravitational field does work because it changes the energy and also the spring. So the answer to 7 is yes. because it applies a force and changes the way the energy look. So that's how you know if it does work. Work is a change of energy by a force. The spring applies a force and changes the way the energy looks. Right before it hit here, it had some kinetic energy and it went from all kinetic to elastic. Eight says, in the real world, friction is a real issue if it rolls from A to D and then it comes all the way back. If there was no energy loss to friction, it would start at a height of 30 meters, roll down, hit, and roll all the way back. But in the real world, friction is a real issue. So it says, I want to know how high up would it go if you lost 10%. Okay, if you lost 10%. So let's do it in a pie chart form. Oh my gosh. What happened there? Good enough. So this is A, and this is A again, or going back toward A. We know to start, it's all gravitational energy. That's originally. It hits the spring and then comes back. But if it's generating some thermal energy, what's happening? If there's friction, it's generating thermal energy. Do you have as much gravitation when you get back? And the answer is, you do not. You have less. Here you had 30,000 of gravitational energy. You've lost 10%. 10% of this is going to be 3,000. So you have 27,000 of gravitational energy and 3,000 of thermal energy. So this is all gravitational. This is gravitational. This is your thermal. And if you want to know how high you went, you're going to set your gravitational energy equal to mgh. This is 27,000. The mass is 100. The gravitational field strength is still 10. Solve for your height. Height is 27 meters. Okay, there's one more. Number 9 says, how did it get here? It got pulled up by some, let's say it got pulled up, by some motor down here, right? It wants to know how much power output there was. Well, what do we know about power? Power is the change in the energy divided by the time. So if the cart went from here to here, what kind of energy change do we have? Well, it looks like we have a change in the gravitational energy. And now I think we know how much gravitational energy is there, right? Isn't it the 30,000? And how much time? It says it's 1 minute, but we have to work in seconds, so that's 60 seconds. And so the power is equal to 500. That's joules per second, and that's watts. All right, there's working energy assessment 2.